All right, we're going in a different direction for the last couple minutes here, okay? We're going to talk just briefly about real gases. We said when we introduced the ideal gas model that it's a limiting case, it's a limiting law, right? The assumptions or the postulates of the kinetic theory are not strictly speaking true, right? We said, for example, that the molecules don't exert any forces on one another. If that were true, then everything would always be an ideal gas. It would be impossible to make a solid or liquid, right? That's not the world that we live in, and that's probably a good thing for us, right? And so we also said that the time where we think the ideal gas law should fail is if the pressure is very high or if the temperature is low, where low means relative to whatever the boiling point of the gas in question is. So at extreme conditions, there are more complicated equations that work better and that are often just required because the ideal gas law doesn't do a good enough job. Right? People in chemical engineering, in chemical plants, for example, often move things around at very high pressures because they want to move a lot of material through a reactor in a short time. Having the pressure be high is a good way to do that, right? And so they will often have to use real gas equations to do calculations for things related to those situations. The real gas model that is most commonly used, at least in chemistry, is what is known as the van der Waals equation. Okay, the van der Waals equation is written there. It's obviously somewhat more complicated than PV equals nRT, right? The van der Waals equation, in addition to PV and nRT, has in it two other parameters. It's got an A over here and a B over there. Those two parameters are what we call the van der Waals constants, okay? They make corrections for the things that are weaknesses in the ideal gas model. The B constant is relatively easy to see what it's doing, right? The B constant here is shrinking the volume that's available to the gas by a little bit. That's because it's saying the molecules themselves take up some space. So that B is accounting for how much room do the molecules take up. It's multiplied by N because the more moles are in there, the more molecules there are, and the more volume, the more the container volume will be occupied by the molecules. The A term is a little bit harder to tease out from what it says there, right? It actually corresponds for the fact that there are non-zero forces between the molecules, okay? What that does is it accounts for the fact that when the molecules collide, they actually have a little bit of a tendency to stick together. So the collisions are not really entirely like billiard balls bouncing off of one another. They're a little bit like they stick and then they separate, okay? That A piece in there corrects for that and fixes up the equation so that it works better. Those two parameters, really, it just gives us two parameters we can adjust for the gas we're talking about, all right? The most complicated thing about the equation is not the form it's in, it's actually the fact that those A and B parameters depend on what gas you're talking about. So unlike R, which is just, it's literally called the universal gas constant, those A and B are molecule specific. So if we're gonna have to use this equation, we would need to look up a different value of those A and B terms for each molecule that we wanted to think about. Okay, so it's more work. There are other real gas equations. A lot of some engineering fields, you might meet up with something known as a virial equation of state, which is another way of describing and correcting the ideal gas model a little bit. All these different models, what they do is they give us some extra parameters, right? By introducing A and B, that lets the equation fit some deviations from the relatively simple behavior predicted by the ideal gas law. I'm not going to do a problem doing a calculation with this. I might give you one in your homework just for fun, but it's not. It's just doing an algebra problem with a somewhat more complicated equation, right? I am going to show us some values of those A and B constants so we can see if we can make sense of them and what they might tell us about some molecules. Okay, this is, as it says up there, a table from the textbook. It has some values of the van der Waals constants for, as it says, several common gases. So let's just see what they look like. If I look at, let's look for small values first. If I scan down that list, and if you scan down that list, you will see that the smallest value for both parameters shows up here for helium. Right? That makes sense, right? Helium is a monatomic gas, meaning a molecule of helium is just a helium atom. Helium's a pretty small atom anyway. It's atomic number 2, right? It doesn't have a lot of subatomic particles in it, not a lot of protons, electrons, what have you, it's just going to be little. It's also got the lowest boiling point of anything, right? The boiling point of helium is about 4 Kelvin. So we think those helium atoms are really, really close to not interacting with one another. That's why their parameter, their A parameter is so small. The B parameter is small because a helium atom is physically very small. Look below that at hydrogen, H2. It's also very small. It's got another very small value. Look for things that have big values of the different parameters. You'll notice that over here, hydrogen fluoride, HF, has a sort of crazily high value for the A parameter. That means those HF molecules have a tendency to want to stick together quite a bit. In, gosh, chapter 6 or so, 7 maybe, when we talk about, no, I guess chapter 8, we talk about interactions between molecules. Sorry, we will maybe make mention of something called hydrogen bonding, which is what accounts for the fact that those hydrogen fluoride molecules stick together quite a lot. We'll see, for example, there's water on the bottom of the list. Water has a pretty large value for this. Water molecules also have a tendency to want to clump together, again, because of that same hydrogen bonding effect. What else is in here? If I look at, I'm looking for, see what I've got that's big. Over here, I've got SO2 has a relatively large value for the size parameter there, right? Sort of makes sense that that would be a larger molecule because sulfur is by then a fairly big atom, right? So from these constants, we can get some ideas about how large would the molecules be. Later on, when we learn some things about the forces between molecules, we'll come back and revisit this table and rationalize what's going on in the column of the A values and what that tells us about how strong the different kinds of forces between molecules might be.